although think of the dot product or introducing the idea of the dot product in terms of a force vector and an angle between the force vector and the displacement vector, and introducing the idea of work, that's a good way to introduce the idea of a dot product, and it's a nice application of it. But we're not always dealing with forces and displacement, and we don't always have vectors that we know the magnitude of directly, and so forth. So what we want to do is think about the dot product in component form. So consider two vectors that are given to us in component form. So I have vector A, which is A1, A2, and A3, and vector B would be B1, B2, B3. And I want to take the dot product of A dot B, because there are other applications of the dot product other than work. Well, how am I going to do this with two vectors that are in component form? Well, what I can do is I'm going to draw my first a triangle here. So let's just say that this is vector B, and over here is vector A. And then this vector right here is going to be actually vector A minus B. And then this is, of course, theta, my angle between A and B. So what I'm going to do is I'm going to apply the law of cosines. And when I do that, and the reason I'm going to do this is because this is the angle here is not a right angle. If it was a right angle, the story would be different. So I want to do this, in general for any angle. So the magnitude of A minus B squared is equal to the magnitude of A squared plus the magnitude of B squared minus 2 times the magnitude of A times the magnitude of B times cosine of theta. That's applying the law of cosines to this angle. Now, I'm just going to do a bunch of algebra, basically. So this then means, to see here, that the magnitude of A minus B squared is equal to the magnitude of A squared plus the magnitude of B squared minus 2 times this is actually nothing more than A dot B. That's good, because remember, I'm trying to get at a way of solving for A dot B when I don't have this force and displacement vector idea. So solving for A dot B, that implies that A dot B is equal to the magnitude of A squared plus the magnitude of B squared minus the magnitude of A minus B squared divided by 2. I probably should have written that as times a half. So let's take a look at these magnitudes now. Now I'm going to work in 3 space because my example here is A1, A2, A3. So this is saying that A dot B is equal to, the magnitude of A squared is going to be A1 squared plus A2 squared plus A3 squared. Let me make that look a little bit more like our actual A3 squared. Now, the magnitude of A would be the square root of this, but it's the magnitude of A squared, so when I square it, the square root goes away, plus the magnitude of B squared, so that's going to be B1 squared plus B2 squared plus got my super and subscripts turned around there, B3 squared. Now I need the magnitude of A minus B. So this could be plus A1 minus B1 squared plus A2 minus B2 squared. Yeah, I think you can see where this is going in terms of algebra. plus this last one, a3 minus b3 squared. And this is all divided by 2, which I'm going to write this as multiplying it by a half. We will hold on to that half for a while here. Now I need to expand these guys. So when I do, see, I'll get 1/2 times a1 squared plus a2 squared plus a3 squared plus b1 squared plus b2 squared plus b3 squared plus, this is going to be a1 squared minus 2a1 b1 plus b1 squared. And then, whoops, I need to, let me see here. I've got that negative. So I'm going to take this whole thing right here, make that minus all of that. There, that straightened it out. So then I'm going to replace this plus with a minus and put all of this inside here. See, plus I'm going to have, see, a2 squared minus 2a2 b2 plus b2 squared. And then this last one, see if I can fit it in here, a3 squared minus 2a3 b3. Nah, it's not that go quite fit. Yeah, I can. b3 squared. There we go. I need one more paren. Sorry. What I'm going to have is that a dot b equals 1/2 times, let's see, a1 squared plus a2 squared plus a3 squared plus b1 squared plus b2 squared plus b3 squared minus a1 squared plus 2 times a1 b1 minus b1 squared minus a2 squared plus 2 times a2 b2 minus b2 squared minus a3 squared plus 2a3 b3 minus b3 squared. Whew. Okay, now a1, I have a positive a1 and a negative a1 squared, so those are going to go away. a2, I have a positive a2 and a negative a2, those go away. a3, I have a positive a3 squared and a negative a3 squared, those go away. See, b1, I have a positive b1 squared and a negative b1 squared, those go away. b2 squared, I have a positive and a negative, and b3 squared, I have a positive and a negative. And then what does that leave me with? That leaves me with the dot product, a dot b equals 1/2 times what's left, 2 times a1 b1 plus 2 times a2 b2 plus 2 times a3 b3. These 2's are all going to cancel out. So what that gives me is that the dot product a dot b in component form is going to be equal to a1 b1 plus a2 b2 plus a3 b3. That's a nice result. It took a little algebra to get there, but that is really a very, very nice result. So what this is really saying, that if I take the dot product of two vectors in component form, all I have to do is take the sum of the product of the corresponding components. It's that easy.